Okay, so I don't want to go into partial discharge theory too much, and in fact in future sessions I may do some very detailed and dedicated partial discharge theory sessions. However, what I wanted to do is give a brief overview of partial discharge. There is a wealth of knowledge out there, and equally if anyone's got any questions afterwards, feel free to ask. But partial discharge is an electrical discharge that doesn't completely bridge the space between two conducting electrodes. Essentially, if you've got a conductor and you've maybe got another phase, or you've got the earthing point, so two electrodes essentially, a partial discharge is a discharge occurring in between those. So not completely bridging the gap, but occurring at some point in between them. It's a point of electrical stress. It's a point where PD is occurring. I'll go through it in a moment. So PD can occur phase to phase or from phase to earth. So depending on where the defect is, where the problem is in the network, depends on where it occurs. But it can basically occur where you can get a point of electrical stress. So naturally that can be between two phases, heading in different directions if you like, or it can be between phase and earth. It can be in gas-filled voids in solid insulation. It can be in bubbles in liquid insulation, or around electrodes in air, which is sometimes can be corona, but can also be surface tracking. So on switchgear, so IPEC tend to focus it on switchgear and cable. Naturally, on switchgear, you tend to get, we classify really as two types. So the first one is surface tracking. So that's when you've got maybe contamination on the outside of an insulator. So you'll get some surface tracking activity, so electrical tracking over a contaminated insulator. The other type is internal discharge. So that's where you've got a defect inside a solid insulation. Maybe you've got a crack. Maybe you've got a gas-filled void problem from manufacture, or like I said, a crack from damage of insulation. And that's an internal discharge. Now, as you can imagine, with both of those, as you know, with both of those defect types, they can occur across different parts of the network. So they can occur anywhere within a switchgear, if you like, because obviously you've got high voltage running throughout the switchgear, you've got insulation throughout the switchgear, and any component of that insulation could be damaged, which could cause a partial discharge to emerge. Surface tracking is most commonly probably found inside cable terminations, but it can of course occur on bushings and any other sort of where there's a high voltage and then a neighboring open surface. Internal discharge can occur anywhere inside cable terminations, if they're solid terminations, inside the end of cables, inside circuit breakers, inside CTs, VTs, so all different components of the equipment. When it comes to underground cables, the two areas that we see PD activity really, joints and accessories are by far the most common place to see PD activity. In XLPE systems, so modern cable systems, probably 99, if not 99.5% of PD will be inside the joints. Manufacturing processes now are very accurate, so pure cable PD is very unlikely, and if it occurs, it's probably detected at the time of commissioning or detected at the time of manufacture even. But in the joints and accessories, that's where we're going to find the problems in cable networks. So 99% of PD will be inside joints and accessories. You do get PD in the pure insulation. It can happen. It's much less common with XLPE, like I say, but if you're looking at oil and paper cables, so the older cable types, we still have a lot of that in the United Kingdom, for example, you can find a lot of PD occurring in the oil and paper. However, it's not necessarily always a concern, and I'll come on a little bit about that later. Okay, so the next few slides really go through the mathematical side of PD and why they occur. So I'm not going to go into too much detail, but I will highlight the sort of main impact. So if we take our sort of ideal case, if you like, which is a solid piece of insulation with a perfect defect inside that insulation. Actually, what we're looking at here, why a PD occurs, is not because there is, say, a gas-filled void. It's not because there is gas within the insulation that's causing a lower insulation level. The problem is that the combination of your XLPE or your polymer, your traditional insulation, with a different material, with an air gap, causes an area where you can get an increased point of stress. So the easiest way to explain that is if I look at this slide here. So the the breakdown strength of air is 3 kV per millimeter. So over a 20 millimeter air gap, that could withstand a 60 kV insulation. The breakdown strength of this polyurethane, this XLPE essentially, is 10 kV per millimeter. So over a 20 millimeter insulation, that could handle 200 kV. However, the problem is that because you've got a combination in our defect here, because you've got some XLPE, then you've got a gas-filled void or an air gap, and then you've got more XLPE. What that means is instead of a uniform dissipation of the energy from the conductor, instead of a uniform dissipation, you get a localized area of capacitance, you get a localized area of stress. So what it means is as the energy in the power cycle increases, the stress very specifically at that defect point increases also. And as that stress increases within normal working voltages, you will get a very small low energy breakdown across that defect. So it must be noted that breakdown is at the defect. It's not across the whole space, if you like. It's just very locally at that defect, and it's a very low energy breakdown. You wouldn't notice it in your electricity network. But what the problem comes from, it acts within working volts. So if we did run through the mathematics, what we would find is that the breakdown strength in this example here is 17.25 kV. So what that means is, whereas, like I said, air would normally withstand 60 kV, the XLP on its own can withstand 200 kV. A combination of the two, this very small air gap, means that at 17.25 kV you get a very small discharge occurring very locally just inside this defect. And so that's what a partial discharge is. It's partially discharging, it's discharging inside that defect. Now the discharges themselves are very low in energy, but it is that repetition in that localized area over time which causes the problems. So as we said, at 17.25 kV is when there's a breakdown, and so this diagram is a little bit complicated, but if you imagine this line here as the line at which the breakdown occurs, so this is our 17.25 kV charge, if you like. What happens is, as the energy in the power cycle is increasing, so if my laser pointer is much easier to demonstrate this. So as the energy in the power cycle is increasing, the stress across that defect is also increasing until eventually it reaches that breakdown point, and then it indeed breaks down. Now the energy in the power cycle is still increasing, and so again we'll get a recharge and a breakdown, recharge and breakdown. So what happens is, on the rising edges of the power cycle, the positive go inside and then the negative go inside, we get an increase in charge, a discharge, increase, discharge, increase, discharge, and then we flip to the negative side, and then we get an increase, discharge, increase, discharge. So what it means is PDs have a very specific pattern in the power cycle. So as the energy in the power cycle increases, discharge will occur both on the positive side and the negative side of the power cycle. So on the right hand side is images that people might be quite familiar with. This is called a PRPD, phase resolved partial discharge, and it's PD patterns in the power cycle essentially. It's one of the tools that is used within a lot of PD equipment, within a lot of instrumentation, to help you decide if the signal you're seeing is from a genuine PD source or from a noise source. It's this distinctive pattern. So here we can see, all we're looking at here is raw data, and each one of these markers is a PD location, but we can very clearly see PD occurring in the power cycle here. So PD, rising edge of the power cycle, falling edge of the power cycle. This one's flipped around the other way, but it's the same thing, rising edge of the power cycle, rising edge of the power cycle. So as the energy is increasing, that's where partial discharge is increasing. Now, of course, this one here on the bottom right-hand side is a condensed PRPD, which is quite common as well. It's one power cycle on top of another. So it's quite common of instrumentation to have that functionality. So instead of looking at a single power cycle where there may only be one PD, what you want to do is record data over a period of time, put them all together so that you can see this sort of pattern in the power cycle. Okay. So like I said, every time these small PDs occur, they're very, very low in energy, but they're very localized and they're very repetitive. So the defect point is very small, which means that's why they're very localized, but they're very repetitive over time, occurring multiple times per power cycle. Partial discharge activity doesn't vary between power cycle to power cycle, but it can vary over the day, it can vary over the year. So PD activity shouldn't be viewed as something that only occurs once every 20 power cycles, for example. PD is generally either occurring or not occurring. And generally, if there is a variation with load, that could be a variation throughout the day, or it could be a variation throughout the year. And what you generally find is not so much that PD occurs and doesn't occur. What you'll find is throughout the year or throughout the day, you'll get sort of high PD and low PD. So you'll get a variation of the level of PD, if you like. Regardless, those individual PDs then, they cause a combination of mechanical, thermal and chemical damage, so that over time, basically the defect that was started maybe from an installation problem or a manufacturing problem or some damage on the switchgear, the defect will slowly get worse over time until eventually there will naturally be a catastrophic failure of the equipment. How that damage propagates or how that damage progresses. If you imagine in solid insulation, it's quite well known. Electrical tree will form. So over time, the physical damage to the insulation will form an electrical tree until eventually the electrical tree is so large that the insulation can no longer survive the energy coming from the conductor. Surface tracking, if it's on outside of insulation, you get surface tracking, and generally what you'll see is this sort of carbonization on the outside of your equipment, which is evidence. You also see sort of white pitting as well, so evidence of that sort of surface tracking occurring, of PD occurring on the outer surface of equipment. So consequences of PD, first one is of course cable failure. If you've got a failure inside a underground cable, you'll see a loss of supply, you'll see an unplanned outage, increased CI and CML. CI is a UK measurement, customer interruptions. CML is customer minutes lost. Of course, every country around the world has a similar measurement criteria, basically looking at the impact of the power failure on where the supply is, so whether that's customers or whether that's the industrial side of the business as well. So customer interruptions, customer minutes lost, and of course a failure point must be found. So naturally you need to find where that cable has failed with fault location technology in order to then conduct the repair to bring that system back online. Now with underground cables, that can be very problematic depending on where the cable actually falls. Last minute requirements, in London for example, we can get a 24-hour repair order, emergency repair, quickly shutting down a road, digging the road and repairing the cable. Still very costly, still very inconvenient, if you like, for the wider application. Cables aren't too bad though. Quite a lot of cable networks have redundancy, so a failure of a cable means you can often reconfigure the network. If it's a ring configuration, not a problem. If it's a radial network, that's where the problem comes in, because of course a cable failure is then a loss of supply until that cable is fixed. On the switchgear side of things then, this is quite a dramatic picture. On the wall here, this is actually compound from the cable termination. So this is a compound filled cable termination. This is from London, a picture we took in London. Compound filled cable termination. This is the opposite wall, so it's not carbonization from a large fire or something, even though it looks like that. But it is quite a dramatic picture that I like to use so to emphasize the first point, which is when you have switchgear failure, of course, the first problem is safety implications. So within that substation, you may have other engineers working, and so safety is the number one problem. When a switchgear fails, it's quite dramatic, and it can be quite damaging to anybody nearby. The other problem is collateral damage, so not only will that main switchgear be damaged, but it could also damage neighbouring equipment and neighbouring components within your substation. Major disruption, switchgear failures are very costly. They take quite a lot of time to repair, and whilst they are being repaired, of course, the reliance or the redundancy is gone. So most substations have two sides to the bus bar. If one fails, then one bus bar is shut down while a repair is conducted. It means your redundancy is completely gone, relying on one side of the substation to operate the whole network, and it can be very, very expensive and disruptive. Thank you very much for your time. Hope you learned something, and watch out for new information that we'll be sending through. Thank you.